Hello everyone, welcome back to the channel. We're at video 8 now. In the last video, man, that was a long one, we talked about the art of sharding. We talked about how to shatter a single database into 100 pieces so we can handle the sheer volume of the internet. We talked about consistent hashing and snowflakes and dual writing. And if you followed that, you're now in a headspace where you realize that the database isn't a box anymore. It's a cloud. It's a distributed swarm of machines. But today we have to deal with the consequences of that choice. See, there's a recurring theme in this series, and it's something I really want you to internalize if you want to be a senior architect. In software, there is no such thing as a free upgrade. Every time you solve a problem, you create a new one. You're just trading one set of constraints for another. When we sharded the database, we solved the capacity problem. We can now store infinite data, but we created a truth problem. I want to ground this in a very simple, almost trivial mental model. Imagine you have a notebook. You write down your bank balance, $100. If you want to know your balance, you look at the notebook. It's consistent, it's available, it's right there. Now, imagine you're so busy that you need 10 notebooks and 10 people to manage them. If I give person A $5, they write it in notebook 1. But if you walk up to person B and ask for the balance, and they're looking at notebook 5, what do they say? If the two people can't talk to each other, maybe the hallway is blocked, then person B has a choice. They can either tell you, I don't know, giving up availability, or they can tell you the old balance, giving up consistency.
This is the core of the CAP theorem. It sounds like a dry academic concept, but it is actually the fundamental law of the physics of information. It is the speed of light of system design. And today, we're going to spend a lot of time, probably more than you think we need, teasing out the nuance of this. We're going to talk about Eric Brewer's original CAP conjecture. We're going to talk about why the Pick 2 meme is actually a bit of a lie. We'll move into the PACLC theorem, which is the pro version of CAP. And finally, we'll look at what eventual consistency actually looks like in the real world, how we build systems that are mostly right most of the time, and why that's actually the only way the internet works. Part 1. The impossible trinity, CAP basics. So let's define our terms. I know you've probably seen the Venn diagram on Wikipedia, but let's look at it from a first principles perspective. CAP stands for consistency, availability, and partition tolerance. First, consistency, C. In the context of CAP, consistency means linearizability. It's a very specific, very strict definition. It means that every read receives the most recent write or an error. Think about that. If I update my profile picture and the database says success, then every single person in the world who looks at my profile 1 microsecond later must see the new picture. No exceptions, no ghosts of the old picture. It's as if the entire distributed system is acting like a single machine, one brain, one truth. Second, availability, A. This means that every request receives a non-error response, without the guarantee that it contains the most recent write. Basically, if I ask the database for data, it has to give me something. It can't just time out. It can't say, I'm busy. It has to be responsive. This is usually measured in nines, 99.999% uptime. An available system is a system that never says no to a user. Third, partition tolerance, P. This is the one that confuses people. A partition is just a fancy word for a network failure. A cable gets cut, a router crashes, a data center in Virginia can't talk to a data center in Oregon. Partition tolerance means the system continues to operate despite an arbitrary number of messages being dropped or delayed by the network between nodes. Now, here is the Pick 2 rule that everyone learns in school. They say you can have CA or CP or AP, but, and this is the first big aha moment for today, CA is a lie. Let me explain that. You can't actually choose CA. Why? Because you don't get to choose whether or not the network fails. The network is a physical thing. Backhoes dig up fiber optic cables. Switches fail. Software bugs cause packet loss. Partitions will happen. If you are building a distributed system, meaning you have data on more than one machine, you must be partition tolerant. It's not an option. It's a requirement for existing in the physical world. So the real choice isn't pick 2 out of 3. The real choice is, when the network fails, do you choose consistency or do you choose availability? That's it. That's the whole theorem. If the link between node A and node B is broken, if you choose consistency, CP, you must shut down node B. You say, I can't be sure I have the latest data from node A, so I'm not going to answer the user. You prioritize truth over uptime. If you choose availability, AP, you keep node B running. You say, I'll give the user whatever data I have, even if it might be old.
I want to take a side quest here into the physics of why this is so hard. Junior devs often think, well, I'll just buy really expensive networking gear so the partition never happens. No. You can't outrun the speed of light. Even if your hardware is perfect, you have latency. In a distributed system, for node A to know what node B did, a signal has to travel through a wire. That signal moves at roughly 2/3 the speed of light. If your nodes are in the same rack, that's nanoseconds. If they are across the Atlantic, that's 100 milliseconds. Now think about what happens when a node gets slow. Maybe the Java garbage collector kicked in and the CPU is frozen for 2 seconds. Or maybe the network buffer is full and packets are being delayed. From the perspective of node A, there is no difference between a node that is slow and a node that is dead. If node A sends a message to node B and doesn't get a response in 500 milliseconds, is the network cut or is node B just busy? Node A doesn't know. It can't know. This is the fundamental uncertainty of distributed computing. So a partition isn't always a cut cable. A partition is any time the delay between nodes exceeds your timeout. And because we want our apps to be fast, we set our timeouts low, which means we are constantly triggering mini partitions. This is why CAP is a law, not a suggestion. You are always playing a game of chicken with the speed of light. So let's look at the CP side of the house, consistency and partition tolerance. Who chooses this? Usually it's banks, stock exchanges, and inventory systems. Imagine you have $100 in your account. You go to an ATM in New York and try to withdraw $100. At the exact same millisecond, your spouse goes to an ATM in Los Angeles and tries to withdraw $100. If the bank prioritizes availability, AP, both ATMs might say, sure, here's your money, because they can't talk to each other fast enough to realize the money is being double spent. The bank is now out $100. The bank hates this. So the bank chooses CP. When the Los Angeles ATM can't reach the New York headquarters to lock your account, it says, I'm sorry, this service is temporarily unavailable. The user is annoyed, the availability is gone, but the truth of the balance is preserved. To build a CP system, we use things like distributed locking or consensus algorithms, like Raft or Paxos, which we'll cover in the next video. In a CP system, a write isn't successful until a majority of nodes agree on it. This is called a quorum. If you have 5 nodes, you need at least 3 to say yes before you tell the user success. If 3 nodes can't talk to each other, the whole system stops accepting writes. It commits suicide to prevent a lie. This is the strong consistency model. It's safe, it's comfortable, it's how we've thought about databases for 40 years, but it doesn't scale to the level of a global social network. Now, let's look at the AP side. Availability and partition tolerance. This is the world of Facebook, Twitter, and Netflix. Imagine you like a photo on Instagram. Does the entire global infrastructure of Meta need to stop and agree that you liked that photo before the heart turns red on your screen? Of course not. That would be insane. The latency would make the app unusable. If the data center in Singapore is disconnected from the data center in Oregon, Instagram doesn't just stop working in Singapore. That would be a disaster for their business. Instead, they choose AP. They let you like the photo on the local Singapore server. The server says, "Success, I got it." In the background, it tries to tell Oregon, but if the connection is down, it just waits. It stores that like in a queue and says, "I'll tell Oregon whenever the link comes back up." What's the consequence? Well, for a few minutes, someone in Oregon might look at the same photo and see 10 likes, while you in Singapore see 11 likes. The system is inconsistent. There are two different truths existing at the same time. But here's the thing. Nobody cares. It doesn't matter if the like count is off by 1 for a few seconds. It's more important that the app feels fast and responsive. This is the shift in mindset. In CP, we assume that a lie is a catastrophe. In AP, we accept that a temporary lie is the price of doing business at scale. Now, I want to level you up. If you go into an interview at Google or OpenAI and you only talk about CAP, they'll know you're a mid-level engineer, because CAP only tells you what happens during a partition. But partitions are rare. Most of the time, the network is working just fine. So how do you choose your database when things are normal? This is where PACELC comes in, pronounced PACELC. It stands for Partitioned Availability Consistency, else Latency Consistency. It's a bit of a mouthful, but the logic is beautiful. If there is a partition, how do you trade off availability and consistency? That's just the CAP theorem we already talked about. Else, when the network is fine, how do you trade off latency and consistency? This is the real engineering trade-off. Even when the system is healthy, you still have to choose. Do you want it fast, L, or do you want it right, C? Let's look at a consistency trade-off in a healthy system. Suppose you have a database with a primary and 2 replicas, video 7 style. A write comes into the primary. Now the primary has 2 choices. 1, synchronous replication, C. The primary waits for both replicas to confirm they saved the data before it tells the user success. This ensures that if the primary explodes, the data is safe on the replicas, but it's slow. Your write latency is now the speed of the slowest replica. 2, asynchronous replication, L. The primary saves the data and immediately tells the user success. It sends the data to the replicas in the background. This is fast, but it's risky. If the primary explodes 1 millisecond after telling the user success, the data might be lost forever because it hadn't reached the replicas yet. So PACELC forces you to realize that consistency isn't just a failure problem, it's a speed problem. A database like DynamoDB or Cassandra is usually AP during a partition and EL during normal times. A database like Postgres with synchronous commit is CP during a partition and EC during normal times. You have to decide where your app lives on this spectrum. We've been talking about consistency as a binary. It's either strong or it's not. But in the real world, it's a spectrum. And understanding the spectrum is how you save your company millions of dollars in server costs. At the top, we have strong consistency, or linearization. This is the gold standard. It's what you get with a single-node Postgres or a distributed system using Raft. It's expensive, it's slow, but it's never wrong. At the bottom, we have eventual consistency. This is the most famous and misunderstood model. Eventual consistency doesn't mean the data might be wrong forever. It's a mathematical guarantee. If no new updates are made to a key, eventually all reads will return the same value. It's like gossip. If I tell a secret to 3 friends and they tell their friends, eventually everyone in the room knows the secret. But for the first 10 minutes, the room is inconsistent. But eventual consistency is often too weak for developers. It makes the UI feel broken. So we have these intermediate levels that are actually quite clever. First, read your writes consistency. This is a huge one for user experience. Imagine you update your Twitter bio. You hit save. The page refreshes.
If the system is purely eventually consistent, the refresh might hit a replica that hasn't seen your update yet. You'd see your old bio. You'd think, wait, did it not save? I just hit the button. You'd hit save again, you'd get frustrated. Read your writes consistency ensures that even if the rest of the world sees your old data, you will always see your latest write. We usually do this by pinning a user's session to the same database node for a few seconds after a write. Second, monotonic reads. This prevents the time travel bug. Imagine you're watching a score of a game. You see 10-10. You refresh, you see 10-12. You refresh again, you see 10-10. Wait, what? Did the points get taken away? No, your third refresh just hit a laggier replica than your second refresh. Monotonic reads guarantee that once you've seen a certain version of data, you will never see an older version. Time only moves forward. Third, causal consistency. This is the most human one. It ensures that things appear in the order they were caused. If Alice posts a question and Bob posts an answer, causal consistency guarantees that anyone who sees the answer will also see the question. It prevents the weird response without a prompt scenario that can happen in highly distributed systems. As an engineer, your job isn't just to pick strong or eventual. Your job is to find the weakest consistency model your business can tolerate. Why the weakest? Because the weaker the consistency, the higher the performance and the lower the cost.
Okay, so let's talk about the messy middle. Suppose you chose an AP system, availability over consistency. A partition happens. User A updates their name to Andre on server 1. User B, maybe a malicious actor or a confused spouse, updates the name to Carpathy on server 2. The servers can't talk. They both say success. Now the partition heals. The two servers reconnect. They look at each other and realize, uh-oh, we have two different names for the same user. We have a conflict. How do we resolve this? There are a few ways, ranging from dumb to brilliant. 1. Last write wins, or LWW. This is what most NoSQL databases like Cassandra do by default. Every write has a timestamp. The database looks at the two values and says, this one happened at 10:01 and this one happened at 10:02. The later one wins. Delete the old one. It's simple, it's fast, but it's dangerous. Remember video 1? Clock skew is real. Server 2's clock might be slightly ahead of server 1's. A later write might actually be an earlier write. You can lose data silently. 2. Vector clocks, or version vectors. This is the senior engineer way. Instead of relying on a wall clock, we use a logical clock. Each node keeps a counter of how many times it has seen a version. We can look at two versions and say, this version is a descendant of that version, or these two versions happened simultaneously. They are concurrent. If they are concurrent, the database doesn't try to be a hero. It stores both values and tells the application, hey, I have a conflict. You deal with it. This is what Amazon's original Dynamo paper did. When you went to your shopping cart, if there was a conflict, you might see both the items you added and the items your spouse added. It's better to see a duplicate item than have an item vanish from your cart. 3. CRDTs, or conflict-free replicated data types. This is the cutting edge. It's a bit of beautiful math. A CRDT is a data structure designed so that no matter what order you receive the updates in, and no matter how many times you receive them, everyone will eventually arrive at the same state without a central coordinator. Think of a set. If node A adds apple and node B adds banana, the merge operation is just a union. Apple plus banana equals apple-banana. It doesn't matter who did what first. The result is deterministic. This is how modern collaborative tools like Figma and Google Docs work. They use CRDTs to let multiple people type in the same document at the same time without a central server having to lock the file. I want to talk about availability for a second, because junior engineers throw around the term high availability like it's easy. In an AP system, we strive for 5 nines, or 99.999%. Do you know how much downtime that is? That is 5 minutes and 15 seconds per year. If your database takes 10 minutes to reboot after a crash, you've already failed your 5 nines goal for the entire year. This is why AP systems are so obsessed with self-healing. If a node goes down, the system shouldn't wait for a human to wake up at 3 a.m. and fix it. The router should automatically see the node is dead and stop sending traffic to it. The remaining nodes should automatically start replicating data to a new spare node. But here is the CAP catch. The more available you try to be, the more you risk split brain. Split brain is a nightmare scenario where the network is slow and half the cluster thinks the other half is dead. Both halves elect a leader and start accepting rights. You now have two different databases that think they are the boss. When the network heals, you have a massive, possibly unfixable data corruption. So when you design for availability, you have to ask, is being up worth the risk of being wrong? For a social media site, yes. For a nuclear reactor control system, absolutely not. So let's bring this all back to the first principles of system design. We've moved from a single machine to a distributed swarm. We've realized that the speed of light and the unreliability of networks mean we can never have the whole truth and nothing but the truth instantly everywhere. The CAP theorem isn't a limitation, it's a framework for empathy. It forces you to empathize with your users and your business. If you're building a system, look at your data. Is it value data, like money or inventory, or volume data, like likes, logs, or clicks? Look at your users. If the system is down for 10 seconds, do they lose money or do they just get bored? Choose your partition strategy. If you need truth, choose C key, Raft, Paxos, Spanner. Accept that the system will occasionally say no to the user to protect the data. If you need speed, choose AP, Cassandra, DynamoDB. Accept that the system will occasionally show old data and you'll need a way to merge conflicts later. Refine with PACELC. Even when things are good, decide how much latency you're willing to pay for safety, or synchronous versus asynchronous replication. And remember, there is no best database. Postgres isn't better than Cassandra. Postgres is a tool for when you need a single, consistent version of the truth. Cassandra is a tool for when the system needs to stay alive, even if a meteor hits half your data centers. The senior architect is the one who can look at a business problem and say, in this specific case, it's okay to be eventually consistent because the cost of strong consistency is $500,000 extra in cloud fees and 200 milliseconds of extra latency. In the next video, we're going to talk about distributed coordination. We've talked about what happens when nodes can't talk, but how do they talk when they can? How do 100 machines agree on who's the leader? How do we achieve a quorum without creating a bottleneck? We're going to dive into the Raft algorithm. It's honestly one of the most clever pieces of logic in computer science. I'll see you in video 9.